Okay. So correction of reheat factor. Correction of reheat for a finite number of stages in a turbine. For a finite number of stages in a turbine. Okay. Now let's try to draw the TS diagram for it. So the TS diagram is something like this. See, most of the things either TS diagram or HS diagram. So I have my TS diagram and TS diagram with a dome. The dome is something like this. It has a dome, and I want to draw the constant pressure lines. So pressure lines are going like this, which are diverging. Just I want to show some 2 or 3 stages. You can go with either 2 or 3 stages. Now, if I try to expand the steam from a superheated condition, so let me call this as some condition E. Okay, let me call that expansion or A, and I want to expand it. So if I try to expand it isentropically, this is what I want to get. It's a simple straight line. Simple straight line. So this is how the expansion takes place. It may start from, so if I draw the corresponding temperature, let me call this as PA, and this particular temperature, it is some PV. Okay. Now in between, so this is my higher pressure. So let me call it as P1, P2, P3, and P4. So I do have the, see, if you will try to look at the some kind of a saturation lines, if you try to look at the saturation lines, so a correction factor is always based on this saturation lines. Why this particular thing? Maybe experimentally it has been found that the correction factor on the saturation line, say for example, the green line. So this is my saturation line. Your reheat factor is has some kind of relation with respect to your saturation line. Hope you remember that reheat factor values ranges from 1.04 to maybe some 1. Maybe 16 or something like that, depending upon the condition of the steam at the inlet to the turbine, whether it is a dry steam or it is a superheated condition. So higher the number, maybe the efficiency and all will be, but maybe the curve, I think if you go back and look at that, the curve will become more steeper and steeper. Okay, the curve will become more steeper and steeper. So with a lower value of reheat factor, it becomes more flatter and flatter. It's not very low value, but still it because that's how the condition will look like. Now, if I try to go for an expansion, okay, if I try to go for an expansion, so the expansion will follow something. If it follows a simple straight line, okay. Now, if it is the condition is superheated, if the condition is superheated, so this is the curve what I'm going to follow. Okay, this is the curve what I'm going to follow, the blue one. Okay, so let me call this as this is A. This is if I call this as V. If I call this as D. If the condition of the steam at the inlet, so instead of A, if I call this as A dash, if it is dry saturated, okay, so I may be following a curve of this nature. Okay, that's an actual expansion. So it's not a straight line, it's actually a curve. Now, when you have this particular thing, so there is always a correction is required for if I go for multiple stages. How that can be done? Okay, how that is done usually. So if I try to look at it, so now if I try to look at the extra thing, see, this is my actual expansion. If it is dry saturated, so if it is superheated, so this may be the yellow plus the maroon color will be the extra thing. So this is the thing what I could see. There is an expansion. There is this particular thing. There is an extra. Now, if I go for if I go for maybe the second stage, this will be the extra thing. That means actual one. I'm looking at, if it is not an isentropic, this is the thing. If I go for the superheated, so this will be an extra portion which is added. Just I'm trying to, it is not that big actually. So those lines will be, the blue lines and this particular mirror lines will be very close actually. But to make you understand, I written a little bit bigger. Okay. Now if I go for a third stage, so third stage will be something like this. Okay. So this will be the, I'm trying to show you what really the scenario is. So this is what we have. And this is an extra thing. So what we can see here. So if it is a superheated, so I have written all the things. Now, what I can do is that actually I can take the same thing and represent it on maybe a TS diagram in the form of a rectangle. Okay, in the form of a rectangle. What it is actually, so let me draw that. The same thing. So whether it is a superheated condition or it is a dry saturated condition, I can write all those things. So the whole thing, I can draw it as a triangle. Okay, that means this is what I could see. See, this is from A to B. Okay, A to B or A dash to B, or this is actually A to C or A dash C, whatever it may be. Maybe whatever may be the only thing is the triangle size may vary. Okay, now if I take for the first stage, so it will be something like this. If I take for a second stage, it will be something like this. Okay, now, so this is what I could see, and this is what I could see. I'm trying to look at what are the things which I can see. I can look at this particular thing, see the correction of it, see the correction of this particular finite number of stages is very, very important. So I'm going to look at this is the condition line. Okay. So in both the cases, whether it is a superheated condition or a dry condition, whatever it may be, I am going to have finite number of stages, assuming if I go with an assumption that there is a uniform temperature drop in each stage, assuming that uniform temperature drop in each stage, because I'm going for a stage efficiency being constant. Okay. Now, if you look at it, so I have the pressure lines. So if this is my P1, P2, P3, P4, okay, this is my P1, this is my P2, this is my P3, and this is my P4. So that's where we have the pressures. Now, if you look at it actually, this is my height actually. So let me call that as height. So what does it represent? This is my height. Okay, then if you look at it, this will be my width. This is my width actually. Now here, I can do many things. So if I try to look at this particular thing, this is one, it's maybe a small rectangle. Okay, and this is also one more rectangle I have. Okay, this is also two rectangles, maybe of same size or it may be of different size. Doesn't matter. Then added to this, I have certain triangles here. So look at this. This is one triangle. What would have been what I was trying to draw on a simple TS diagram? I can do the same thing on HS diagram also, where it will be an enthalpy and entropy. Okay, this is what I am going to get. I am going to write an equivalent kind of things. So this is for first, second, and third. Now, what is this? What I am trying to show in the maybe in the pink actually, that is the maybe what I'm trying to is an increase in entropy heat drop due to losses. So what will happen actually? This particular thing, see, this should be brought in. See, this should be as much as possible. It should be minimal. Bigger, see, I can easily accommodate. I can easily tell that bigger these triangles, 1, 2, 3, what I'm trying to show, bigger the triangles. So the area, okay, if I call it as the area of that particular triangle. So if I try to take, if this I call this as A, B, C, okay, area of the triangle, area of the triangle. Okay, ABC. So it is half into base into height, that is half into W into H. So let me call this as equation number 1. Okay. Now, what is the shaded portion? So the shaded portion of the area, okay, the shaded area, that is the pink, what I'm trying to show, is equal to area of the triangle ABC, area of the triangle ABC minus, suppose if all the stages are of same temperature drop and same stage efficiency, then 1, 2, 3 will be equal. Okay, 1, 2, 3 will be equal. That means I can write 3 times of half into, see, this will be h by 3, this will be h by 3, this will be h by 3. This will be w by 3, w by 3, this is w by 3. Then I can write half into, this is h by 3 into w by 3. Okay. Now what it will be? So one of the three just cancel out. It will be WH by 6. So it will be, so what will be the shaded area? This will be, area of the triangle is actually W into H by 2 minus W into H by 6. Okay. So this particular area, what I am looking at. So if the reheat factor, okay, the reheat factor, what I consider for infinite number of stages or finite number of stages, if I try to look into that, then if I yeah, what is the thing? Yeah, a reheat factor for uh, a finite number of stages. So the reheat factor will be your WH by 2, that area, plus some isentropic enthalpy drop. Okay, if I try to go with a reheat factor for your finite number of stages, this is what I am going to get. Then the reheat factor for finite number of stages, infinite number of stages and finite number of stages is what we need to look at. Is it possible for me? See, this is the expression what we have got. That is the shaded area is WH minus WH by 6. So now if I take WH outside, if I take simply WH outside, so WH by 2, if I take it outside, this will be 1 minus 1 by 3, or I can take it as WH by 2 into 3 minus 1 by 3, or it is 2 by 3, whatever it may be. Okay. So now, if you look at it actually, WH by 2 into Z may say, now, this 3, what I told, no, this 3, what is this 3? This 3 represents that I have 3 stages. Okay, the 3 represents that it is of 3 stages. What is it actually? Z is, so let us define Z, which is 3 for 3 stages. So I can have a generalized shaded area. Therefore, a generalized shaded area. Because I'm trying to show you 3 stages. If there are 4 stages, if there are 5 stages, then I can have a generalized shaded area, this particular formula, or I can write this will be WH by 2 into, okay, Z minus 1 by Z. Okay, Z minus 1 by Z. So this is your general area, shaded area. This is for a finite number of stages. This is for a finite number of stages. Have this formula. Now, what will happen if I have an infinite number of stages? If I have an infinite number of stages, what is the formula for reheat factor is go back here. What is this reheat factor? The reheat factor is delta HC by delta H isentropic. Okay, delta HC by delta H isentropic. That is what you are going to see the actual one. Okay, then what you are going to see the your isentropic delta H. Now, if you closely observe for isentropic this thing, what is your delta HC? Okay, what is your delta? You are trying to do more amount of work because here I am trying to see here what will happen actually. Your delta HC, this particular thing, what I am trying to do, I can write a reheat factor for infinite number of stages. So, reheat factor, reheat factor, that is RF for infinite number of stages. This will be your area of triangle plus delta H isentropic. This is an extra thing divided by delta H isentropic. Under this condition, I could get reheat factor which will be greater than 1. Which will be greater than 1. Okay. Now, what is this actually? This is for infinite number of stages. This is for infinite number of stages. Or I can write WH, okay, WH by 2 times your isentropic, okay, WH by 2H delta isentropic. If I simplify, what will happen? So if I add minus 1 on one side and plus 1 on the other side, so what will happen? So this will be minus 1. So this will be plus 1 minus 1. So this will be reheat factor. Okay, this will be minus 1. Yeah. WH isentropic, 2 isentropic if I take. So 2 common. If I try to bring in 2 isentropic here, okay, then it will be isentropic. One more will come there. So that will be equal to what it is. I have defined it. Okay. Let me go back and see. So WH by 2 plus delta H isentropic. Yes, I have written delta H isentropic. Yes, fine. Okay. Then I can write this as plus 1. Okay. WH isentropic because this is cancel out. So this will be plus 1. Okay. This is for reheat factor. This thing. Now, reheat factor minus 1. So if I want to do that actually, maybe if I take this to the left hand side, reheat factor infinity minus 1 is equal to WH by 2 times your delta isentropic. So let me call this as some equation number 2 or 3. Okay. Now, if you go back this particular thing, shaded area, what we have. See, the shaded area is nothing but that's also reheat factor for finite stages. So the reheat factor for finite stages and reheat factor for infinite number of stages. So what it will be? The reheat factor for finite number of stages will be, okay, so will be WH by 2. You have this WH by 2, okay. Your delta H isentropic is there. The added one is Z minus 1. Okay. What I'm going to do actually, this wherever you have this WH by 2, no, I will try to substitute this in terms of this thing. So that is your reheat factor. Maybe for a see, I can do I can write the same thing for the reheat factor for finite stages. Let me write it. Reheat factor for, maybe we can call it as RF Z because Z number of stages. I can write. So this will be your W into H by 2 times your isentropic. The extra factor there is actually, this will be Z minus 1 by Z. Same thing. So whatever I exercise I'm going to do, no, the same exercise I want to. This is for infinite number of stages. So then this is for finite number of stages. If I call this as equation number 3, same exercise I want to do. Reheat factor for finite stages, reheat factor for infinite number of stages. Only thing is extra is I am trying to add this z minus 1. If it is 3 stages, it's 3 minus 1 by 3. If it is 2 stages, 2 minus 1 by 2. So now if I try to take the ratio of it, okay. So if I try to take, therefore, the ratio of the reheat factors, if I take it actually, then so that means actually this will be reheat factor. Sorry, this will be plus 1. I missed out. Actually, this is z minus 1 plus 1. Yeah. Then this is equation number 3. Or I can write, if I try to write reheat factor z minus 1, okay, divided by reheat factor infinite number of stages minus 1. This will be what I'm going to get. Actually, if I try to write it, actually this will be WH by 2 times delta H isentropic into, so Z minus 1 by Z divided by WH by 2 times delta H isentropic. So these two things just cancel out. I'm going to get a reheat factor Z minus 1, reheat factor infinite 1. It will be just simply Z minus 1 by Z. So this is the correction factor. Okay, this is a simple correction factor if I go for multiple stages. Okay, if I go for a multiple stages, so I'm going to have little bit of correction factor. This correction factor is only applicable for multiple stages. Multiple stages means more than two. If it is one single stage, so whatever the reheat factor we are calculating, or maybe the last class, whatever it is, that reheat factor is fine. If I go for multiple stages, then the small correction factor I need to add, and this correction factor will give the actual X, because all depends on the thermodynamics. So if you look at your thermodynamics, it tells that my entropy keeps increasing whenever I have an expansion process. If it is expanding, then the entropy has to increase. So now this correction factor, see this number, this correction factor will clearly relate us to the actual expansion processes, the actual expansion process, and which is evident from your thermodynamic concepts. Is that clear? Fine. Okay. So now we'll try to look into the two design procedures. The first one is the design procedure for impulse turbine. I'm going to write in the form of points. Okay. Now, if it is a single stage, if it's a multi-stage. So single stage and multi-stage is what we need to look at. Okay. The sequence of calculations, what we need to look at. Okay. It's an impulse for an impulse turbine. See, whenever you have an maybe single stage or multiple stage, I'm trying to generalize it, single stage or multiple stage. The first thing what we try to look at is actually the output from the generators. Okay. So whenever you want to look at the design procedure, what is the output from the generator? Okay, this will be different from your shaft power output. Different from shaft power, because we do have the mechanical losses, other losses involved. Shaft power is different from the turbine. From that, actually, I have to look at the output from the generator. This is the first thing. The second thing what we have to look at is the speed of the turbine. Speed of the turbine. Okay. Then the third one, the operating, the pressure, the operating pressure and temperatures. Operating pressure and temperatures at inlet. You can call it as P1, whatever it may be. So when you have the inlet at the same time, so your exit pressure or the back pressures. Exit pressure or back pressure. So at exit, this also becomes critical. So these are the four major points which are very much important when you want to design your maybe impulse turbine. Okay. Now, once you know this, actually, you have to do sequence of calculations. Okay, this data is very much required. Maybe a single stage or multiple stage, whatever. But this particular thing is very important even for single stage, multiple stage. These four different. Now for the single stage, okay, for a single stage, let me write it. For a single stage turbine, what is the sequence of calculations? See, you have to calculate the sequence of operations. First thing is you have to calculate the heat drop or enthalpy change. Heat drop or enthalpy change depending upon your pressures. So what is the pressure? It can P1 to P2 or P2 to P3, whatever it may, whatever taken. Okay. Next, second thing. See, you have to calculate the losses. Okay. The losses involved. It can be as simple as isentropic, maybe your hysteresis loss or a pressure loss, or it can be frictional loss, whatever it may be. So all types of losses. Because why this particular loss? Because this losses will reduce your work output. These losses will reduce your work output. So once you're able to calculate these losses, we will end up with calculating the efficiencies. Okay, calculating the efficiencies. Okay, what are the different efficiencies we come across? I'll know that we have, I think we have discussed in the internal efficiency, mechanical efficiency, generator efficiency, all those things. Okay, so let's try to look into that. Internal efficiency, your blade efficiency, your generator efficiency, your mechanical efficiency, all these efficiencies we have to look at. Okay, there's one thing. Once you are able to do this simple preliminary calculations, I need to calculate the mass flow rate. Okay, I need to calculate the mass flow rate that is flowing in the turbine. So mass flow rate involved in the turbine. So that is your m dot. So it depends on maybe your, so P is equal to omega QH, hope that particular formula. So you have that. So you have a delta isentropic into all the efficiencies. Okay, let me put it as overall efficiencies, which is maybe product of internal efficiency, generator efficiency, mechanical efficiency, or maybe your fluid blade efficiency, or all the efficiencies. Okay. Once you know this, now your steam velocity with which entering your nozzle. So that is also very important. Hope if you go back to your steam nozzles, uh, maybe textbook, maybe in the what we studied in your unit 1 or something. So your velocity of the steam that is entering. So velocity of the steam at the nozzle exit or entry to the turbine. If you want to do that, hope you remember that we had this particular formula, derived it, square root of 2000 or root 2gh or something. Okay, so if you go back, you can just look into that in your nozzles and diffusers. We had this formula 44.72 into delta H isentropic into your nozzle correction factor or efficiency, whatever it may be. Okay. Then, see, when you're designing it, your flow angle at the inlet, flow angle at the inlet. So usually it is alpha 1. So this has to be fixed actually. So you can't have a number. This number has to be between your 14 and 22 degrees. You can't have a 25 degrees. You can't, because what will happen is if the number, if the angle is more, the jet gets deflected. Okay. Then once you have this particular thing, I should be able to calculate your blade speed. Okay. If I want to calculate the blade speed, I should know my optimal value of your speed ratio. So for that, what they do is actually, so they try to plot this particular thing. So they try to, for each turbine, they try to do this actually. This exercise they try to do. What they do is actually they try to put this efficiency versus phi. Majority of the time they will try to put either overall efficiency or internal efficiency, whatever it may be, and the curve will go something like this. This is what they're going to do, and this is your maximum efficiency, and the corresponding will be your phi optimal. So from that actually, because phi is equal to is the ratio of blade velocity to this. So I will be able to get my U depending upon this area. For an impulse turbine, I think we have looked at the maximum efficiency is at 0.5 times. So phi is equal to 0.5, you will get this thing. But from the design perspective, this value has been found to be experimentally 0.46 or 0.47. So when you are solving the numerical sum, we take phi is equal to 0.46 and the ideal one is the 0.5. Then once you've done this actually, then they will go for velocity triangles on stage basis. Okay, stage velocity triangles. Stage velocity triangles. Why this velocity? Velocity triangles clearly give an input to the designer regarding the availability of energy at each and every stage. What stage it is there. Okay. Once they do it, actually, they will try to calculate this reheat factor. Okay. Then reheat factor with internal stage efficiency, and they do iterations. They will go back, and this is an exercise. So this is actually an iteration to arrive at the read factor internal efficiency, because already you have calculated internal efficiency, already you have calculated stage efficiency. That has to be optimized. Just now we looked into that. So they try to iterate here and they try to calculate the, so recalculate it again. Read factor is calculated, internal efficiency is calculated, and stage efficiency is calculated, and the overall efficiency. So this becomes an iteration, and they want to do that. Okay. Now, what will happen if I go for a multi-stage? That is more than two, more than single row. Okay. So if that is the case, maybe I don't want to repeat. What I will try to do is actually maybe for multi-stages. So stage 1 to 6 is the same. Okay. So if it is a multi-stage impulse turbine, multi-stage impulse turbine. If I go for a multi-stage impulse turbine, so the steps 1 to 6 remain the same. Now, when you go for the step 7, here what they do is actually here is slightly they do a little bit of different calculations. I can't, if it's a single stage, I'll try to do that. So what they do is, we know this phi is equal to u by v1, and they assume this value as 0.1 to 0.3. See, for a single stage, it is 0.46. But if I go for multiple stage, this value, they will start any number between 0.1 to 0.3, and then they try to optimize it. Then they try to optimize it. Okay. Now the next stage actually, once they do, they try to do the same velocity triangles. Okay, they try to draw the velocity triangles, velocity triangle for all stages. They try to maybe draw the velocity triangle for all stages. Okay. Once they draw this actually, from the velocity triangles, they will try to re-look into your blade efficiencies. Once they draw this triangle, any of our multiple stage, you know this blade efficiency is given by, okay, maybe hope you remember that, VW, maybe 1 plus VW2 plus or minus, depending upon the direction, into U divided by, I think, you have this V1 square by 2. Now, what is this V1? V1 is the inlet absolute velocity. What is VW1? It is the whirl velocity. VW2 is the whirl velocity as it. So, what I can do is actually I can generalize it depending upon I is equal to 1, J is equal to 1 to n number of stages. Okay, this can be I, this can be J. So, this can be I square. So, this is for a multi-staging. So, now once you calculate this blade efficiency, I will try to come back and calculate my internal efficiency, which is completely different from, say, calculate your internal efficiency, which is your blade efficiency minus losses incurred. Okay, minus losses. So it can be all the losses. It can be, see, now the point is when you go for multiple staging, this losses may increase slightly compared to a single stage. Okay. Now this losses has to be reduced. So to do that, what they do actually, they try to optimize your what we call it as maybe your they'll come back. See, from here they try to go back and try to optimize your phi value. Okay. Then at the end they try to look into this reheat factor. They try to look into this reheat factor. Okay, which is depending upon your internal efficiency, which is once again depending upon your blade efficiency. Okay, then they try to iterate it. Whatever I told, no, it is a iteration procedure. It's an iteration. Whatever they were trying to do for the single stage, they do the same thing for a multiple stages. The way it is going to change is actually these two things. The way it is done here, the step 7 and 8, it is little bit different because the blade efficiencies are going to change as I move from one stage to next stage. Is that clear?
Sir,
Yes.
sir, sir,
Yes, listen, tell me.
can we tell that this iteration is done
Can you
based on
speak a
the,
little louder?
sir, this iteration is done based on the phase change of the steam, can we tell, sir? Because reheat factor depends on the like quality of steam, no, sir. So can you hear me?
I lost my connection. 1 minute. Am I audible?
Yes, sir, you're audible, sir.
Yeah. I think I lost connection. I'm back actually. Yeah, tell me, you're asking something.
Sir, this reheating factor you said, no, sir, like will do a lot of iteration. In terms of multiple stage, the quality of the iteration is done based on the quality of steam, no, sir? Because when it is
See,
expanding,
what will happen in case of a multi-stage is actually maybe this quality of the stream will come down because that's why we want to start with a superheated condition stream. So once I go for multi-staging, 3 stage or 4 stage, definitely the quality of the stream we may end up with a wet steam.
yes,
That's
sir.
where the impact it will have an impact on your blade efficiency. What will happen? Your VWs, no VWs will become smaller and smaller. And your V1 or V2, whatever that also will become smaller and smaller because there's a lot of friction involved. That's an actual expansion process. So all these numbers are going to change rather than a single stage to multiple stages. So what I am trying to explain is the procedure, what they try to do, designing it.
Yes, sir.
Yeah, fine. So now maybe the last this thing. So design procedure for impulse reaction turbine. Design procedure for impulse reaction turbine. Okay. So here, anyhow, see the first procedure is the same. Okay, the calculation procedure. Anyhow, here also these four things I told, no? This is more general. Maybe output from the generator, speed of the turbine, operating pressure, back. It is more generalized thing. Anyhow, that is there designed for either for impulse turbine or reaction turbine. These things remain same even for your reaction turbine also. These 4 points remain same. Other than this, actually, where usually impulse reaction turbine, you don't have any single stages. It will be always multiple stages. Impulse reaction turbine is always multiple stages. So what they do actually, the first thing what they try to do is actually, it is the heat drop or isentropic heat drop. Okay, that is heat drop or isentropic heat drop between your pressures P1 and P2 or between P1 and P2. This is one particular thing we have to look at. Okay. Now here, in case of a reaction turbine, pressure losses are very, very critical here. The isentropic heat drop, see, isentropic heat drop is one particular thing. Okay, this pressure losses will have, see, here, the pressure losses has to be cross-checked or verified. And this losses should be between 2 to 5%. I have to design in this factor so that because this have an impact on your actual isentropic. If the losses are more, your actual enthalpy drop will change like anything. Okay. Then once you have this actually, then they will go back and they try to, once you have the losses, they will try to look into the efficiencies. What are the efficiencies? Once again, here also we have the efficiency, that is your internal efficiency, your mechanical efficiency, generator efficiency, whatever it may be, mechanical, generator, or your vane efficiency, all these efficiencies are calculated at that given state point on HS diagram or PS, whatever it may be. Then the fourth point, once again, same thing, they're going to calculate the mass flow rate. The mass flow rate depends on your, what is the power you are generating. Okay, the power you are generating, what I told. Then delta isentropic multiplied by your overall efficiency. Because overall efficiency, it can be a product of internal mechanical generator and all your leakage, blade, all the efficiencies will come into picture. That's why overall efficiency becomes very, very critical here. Okay. Now, see, impulse reaction turbine, the first stage diameter. See, you have an expansion, something like this. If you look at it, the turbine will be expanding something like this. So, okay, this is an expansion. Okay, this is your compression and your expansion. This is your expansion. This is your maybe a compressor. This is how you write, and this is your turbine. Now, this diameter at the inlet becomes very, very critical actually. So the diameter becomes very, very critical here. So what are the things which are very important here? So the things which are very important here is actually your mass flow rate, the specific volume, okay, the angle with which the fluid is entering, okay, the fluid is entering, and also your speed ratio. Speed ratio for a reaction turbine is different from speed ratio for your maybe for an impulse turbine. So it is very critical for the diameter. Diameter is critical. The wheel diameter, we call it as the wheel diameter at the first stage. Okay, the wheel diameter at the first stage is very critical. So if I maybe there's a formula is there. So this form there is no option to derive this formula, but I want to write this formula and will try to explain that particular thing. So you have this particular formula which depends on maybe pi dn by 60, all those things and all. So if you try to 60 times your mass flow rate, your speed ratio, your specific maybe volume divided by pi square into the length. Okay, the length at the inlet. So if I call this as 1, okay, pi square L or L1, whatever it may be, L1 sine alpha 1, alpha 1 is at the inlet and the speed. So this is a simple formula. How they obtain it actually? Maybe using this particular formula, pi u is equal to pi dn by 60 and putting this q is equal to area of the flow into velocity of the flow, and then your phi is equal to u by v1. So using this particular thing, I'll be able to get it. Area of the flow is pi d1 square by 4. So from that particular thing, we're able to get this. Now, what is critical here? Now, the wheel diameter for a first stage, maybe for your uh, first stage of a turbine, is very critical here. Now, this L1 is very critical depending upon the value. Say your L1 is it's designed, it should be between 20 to 25 millimeter if I am designing for a small capacity turbine. And L1 should be a number between slightly bigger, that is 35 to around 40 or 45 mm if I am going for a large capacity turbine. Large capacity turbine. Okay. And what should be value of your speed ratio? It should be 0.55 to 0.8. As I told that for an impulse reaction turbine, your speed ratio will be higher than 0.5. Higher than 0.5. Then alpha 1 here maybe on the lower end value, what it was 14 to 22 degrees for a impulse turbine. Here it will be slightly higher. This will be a number between 18 to 22 degrees. See, all these numbers has been arrived after doing some experiments, optimizing all these things. So that if this number is between this range, actually, then your maybe whatever design aspect, whatever the parameters you are trying to calculate, that will be within a particular range. Then it has been found. See, majority of the times actually they try to look at the first stage and last stage. This is about the wheel diameter of the first stage. Now, if I try to look at the wheel diameter with respect to the last stage, so there's a simple formula they try to use it actually. The simple formula that they do is actually, if the diameter of the last stage, it has to be roughly around 1.5 times of your D1. 1.5 times your, so it has to be diverging. It has to be slightly diverging, roughly around 1.5 times if you keep it actually. So that's a thumb rule. It has been found. On the last stage, so you can call it as maybe greater than, also doesn't matter. It should be greater than or equal. So at least it should be 1.5 times, or it can be greater than your 1.5 times of your inlet diameter. Or you have a specific formula is also there.